In this session, I will prove the Sylow's second and third theorem. Okay, let us first look at the statements of the Sylow's second and third theorem. Okay, so Sylow's second theorem states that if H is a subgroup of a finite group G, and suppose the order of H is a power of a prime P, then H is contained in some Sylow P subgroup of G. Further, if you have any two Sylow P subgroups, they are conjugates. The third Sylow theorem tells us that if P is a prime and G is a group of order P raised to K times M, where P does not divide M, that is P raised to K is the highest power of P that divides G, the order of G, then the number of P Sylow subgroups of G is congruent to 1 modulo P, and it divides M, the number of P Sylow subgroups. So the third Sylow theorem is about the number of P Sylow subgroups. So the second theorem talks about two Sylow P subgroups are conjugates. Okay, so this is the difference. Now I would like to make one statement which is written in Fraley, that is, do not underestimate a theorem that counts something. Okay, this is a nice to keep in mind. These theorems are very important when it comes to your net papers or just your understanding of the subject. Okay, so let's go on to the proof of the second Sylow theorem. Okay, so I'll tell you the idea of the proof of the second Sylow theorem. The first thing which we will do is we will look at the set of conjugates of a Sylow P subgroup, say K, and we will show that H is lies inside one of the conjugates of that. Now notice that every conjugate of a Sylow P subgroup is a Sylow P subgroup, because we know that conjugates of subgroups are isomorphic to the subgroup itself and hence have the same number of elements as the subgroup. So let us start the Sylow P subgroup. We know that a Sylow P subgroup exists by Sylow's first theorem. So we can start with a Sylow P subgroup. So let K be a Sylow P subgroup. So let K be a Sylow P subgroup, and I will take C to be the set of all conjugates of K. Now notice that as G is a finite group, the set of all subgroups of G is also finite, and hence the set of all conjugates of K, which are subgroups of G, is also going to be finite. So we will let C be the set K equals K1, K2 up to Kn be the set of distinct conjugates of K. Okay, and we are going to prove that H is a subset of one of these conjugates. So let us see how we proceed with the proof. So we will use the functions which were defined in the lemma. Okay, so let SC be the group of permutations of the set C. Okay, group of permutations of the set C. And by the two lemmas which we have proved earlier, we know that this function t from G to SC defined by t of G equals phi G is a homomorphism. Okay, so we know that this here is a homomorphism. Let us consider this homomorphism, and we need to show that H lies inside one of these. Therefore, using the lemma again, we basically need to show that there is some I such that the orbit of Ki has only one element. This is what we are going to aim at. This is what we had proved in the lemma, that this happens if and only if H is a subgroup of Ki. So this is what we will use to prove. Okay, so somehow we need to show that there is at least one orbit such that the number of elements in this orbit is 1. So let us see what we know. We know that the number of elements in TH divides the number of elements in H. We also know by the orbit stabilizer theorem that the number of elements in TH is equal to the number of elements in the orbit. For any I, this is true, number of elements in the orbit of Ki into the stabilizer of Ki. Which means that the number of elements in the orbit of Ki divides the number of elements in TH, and hence this tells us that the number of elements in the orbit of Ki divides the number of elements in H. But here we know that the number of elements in H is a power of a prime, which means that the number of elements in H is either 1 p square, p raised to 2, p raised to 3, or something like that. So this means that the divisors of such numbers can only be of that same type. That means they have the same primes. Hence, the divisors can only have prime divisors which are there in the number itself. So therefore, this will tell us that the orbit of TH, orbit of Ki, has either 1 p square or something of that sort, p cube, something of that sort. And this happens for every I. Okay, so for any of the orbits, this is going to be true. Now, the next thing we notice is that the number of elements in C or the orbits partition C, which means that the number of elements in C is going to be the number of elements in the distinct orbits. So when I write this sum, I mean the distinct orbits. I'm talking about the distinct orbits. So let us try to understand what we have reached at. We want to show that one of these is 1. Okay, we want to show that one of these orbits has a single element in it. What happens if it does not have a single element in it? If it does not have a single element in it, it means that it is going to be some power of p. So suppose none of these, suppose the orbit of ki is not equal to 1 for every I, then it means that P always divides the number of elements in the orbit. Okay, which means that P will divide the sum, and hence P divides the number of elements in C, or that is N. Okay, so this is the first thing we notice, that if this is never 1, then P has to divide N. Now, what is N? N is the number of conjugates of K, but we have proved that the number of conjugates of K, that is N, is equal to G by Nk, which means that the number of elements in G is equal to the number of N times the number of elements in K, Nk. Okay, let us understand this here now. Now, suppose the suppose the number of elements in K is P raised to K. Okay, suppose this is P raised to K, then the number of elements in G will be P raised to K times some M, where P does not divide M, because K is a P Sylow subgroup. Hence, the number of elements in P is the highest power of P that divides the order of G. So this means that P does not divide M. Also, you know that the number of elements in K should divide the number of elements in Nk, because K is a subgroup of Nk. So this means that the number of elements in Nk will be equal to some P raised to K. It will be a multiple of the number of elements in K. That is P raised to K times some, say, R, where, okay, that is not clear in this case. Okay, so therefore, what we have here is write the number of elements in G in two different ways. We have the number of elements in G is either N times P raised to K times R, and also you know that the number of elements in G is P raised to K times M, which will tell us that, okay, from these two equations, you can cancel out P raised to K, you will get NR is equal to M. But here you see that P does not divide M, which means that P cannot divide N, because if P divides N, then P will have to divide M, but that is not true. Hence P does not divide N. And what we have got here is, we have got a contradiction to this statement that says that for any I, the orbit of Ki is not 1, and therefore we see that there exists I between 1 and N such that number of elements in the orbit is equal to 1, which would mean that H is a subgroup of Ki by our lemma. Now, what is left to prove? The next thing which is left to prove is that any two Sylow P subgroups are conjugates. Now notice here that if H is a Sylow P subgroup, this would mean that the number of elements in H would be p raised to k itself, which is the number of elements in K or the number of elements in Ki, because Ki is a conjugate of, in fact, Ki itself is a Sylow P subgroup. So this will mean that the number of elements in K is equal to the number of elements in Ki, which is, and you also know that H is a subgroup of Ki. Okay, because remember that H is a Sylow P subgroup, means that the order of H is a power of prime. It's p raised to k. Hence, this will hold for some I. And therefore, now the number of elements is the same, but this is a subset of this, which means that H has to be equal to Ki. But Ki is a conjugate of K. Hence, H and K are conjugates. So this proves the second part of the theorem. So this proves our Sylow's second theorem. Let's move on to prove the Sylow's third theorem. So let us look at the statement again. What does the statement say? So if P is a prime and G is a group of order P raised to K times M, where P does not divide M, then the number of P Sylow subgroups of G is congruent to 1 mod P and it divides M. Okay, let's try to look at this proof. It is not very difficult. So let us start with a Sylow P subgroup. So let K be a Sylow P subgroup. Okay, and we'll take C to be the set of all conjugates of K. So let be K equals K1, K2 up to Kn be the conjugates of K. Now, by Sylow's second theorem, this will mean that by Sylow's second theorem, we know that any two Sylow P subgroups are conjugates, which means that the set C is essentially just the set of all Sylow P subgroups of G. So this will mean that C is the set of Sylow P subgroups. Now, let us consider the same function again, which we had considered in the previous theorem, and the lemma, that is T from G to SC, given by T of G equals phi G. Notice here that let us look at the orbits, but with respect to the group, the permutation group, T K itself. Okay, so T of K. So we see here that the number of elements in C, or N, which is the number of elements in C, will be equal to the sum of orbits T K this time of Ki. Okay, so this is now let us notice this here. If I is 1, that is for the orbit of K is going to be just 1, because K is a subgroup of itself, and we know that if K is a subgroup of itself, the number of elements in the orbit is 1. So this will basically be 1 plus summation where j is not equal to 1. Okay, so these are again distinct orbits, even though I am not writing here. Now notice these orbits. Is it possible that any of these are 1? Okay, so it is not possible that any of these are 1, because if these are 1, it means that K is a subgroup of Ki. But this cannot possibly happen because they are Sylow P subgroups and hence they have the same number of elements, which would mean that K is equal to Ki. But that is not true. K is equal to only K1. K cannot be K2, K3 or Kn. So that is not possible, and therefore none of these can be 1. But the possibilities for these, like we have seen in the previous theorem, is only 1 p square, because this should divide the number of elements in t of k, but the number of elements in t of k divides the number of elements in k, but the number of elements in k is p raised to k. Hence this can only be either 1 p square up to p raised to k. So we know that none of this is 1, therefore p divides the sum, and hence this tells us that n is congruent to 1 modulo p. Okay, so the first part is proved. We have in fact proved the so we have proved the first part, that is the number of Sylow P subgroups is congruent to 1 modulo p. N is the number of Sylow P subgroups because it's the conjugates of k, so it's the number of Sylow P subgroups. So n is congruent to 1 modulo p. The next thing we have to do is prove that n divides m. So let's see how we prove that n divides m. Okay, so again with the same idea, we know that n is equal to g by nk. Okay, which means that the number of elements in G is equal to the number of element n times n of k. And as we have seen earlier, since the number of elements in k divides the number of elements in nk, we have the number of elements in nk will be p raised to k times some t. Okay, so this tells us that the number of elements in G is n times p raised to k times t. But we know that the number of elements in G, it is given to us as p raised to k times m. So therefore this tells me that looking at both of these, you have n times t is equal to m. Okay, and since n times t is equal to m, we have n divides m. So this completes the proof of the third Sylow theorem. Okay, now we'll prove a small corollary from the Sylow theorems. Okay, we will show that Sylow P subgroup is normal if and only if there is a unique Sylow P subgroup. So suppose there is a unique Sylow P subgroup. Suppose G has a unique Sylow P subgroup. Okay, so what does this mean? This means that since K is given to be the Sylow P subgroup, it means that K is the unique Sylow P subgroup. So this means that now you look at any G in G, we know that conjugates of Sylow P subgroups are Sylow P subgroups since they are isomorphic to the subgroup itself. So that means you give me any G in G, Gk, G inverse cannot be anything other than K itself, because that is the only Sylow P subgroup. And this means that K is normal in G. Okay. Conversely, suppose we assume that K is normal in G. What does this mean? This means that you give me any G in G, the conjugate of K is K itself, which means that we know that the set of all conjugates of K is the set of Sylow P subgroups. But here we are saying that